Hello, my dear students. On this video, I'll be talking about our test one, which was regarding the topic of equilibrium. So listen up, take your pen and paper, and let's move along together. So in the first question, I am talking about as kind of systems. We have covered this in our PowerPoints that the system where there is energy transfer and matter transfer happening is called open system. And the system where there's no energy transfer or matter transfer, it's called isolated system. Okay, now we move on to the second one. It's telling us as the forward and reverse forces are occurring at equal rates. The concentration of liquid and gas does not change, but molecules are constantly being introverted between two phases. This is described as static equilibrium. This is wrong. We said that it's called dynamic equilibrium because there is constant exchange. You see, like it's continuing, but the overall concentration is not changing. Overall concentration is not changing, is constant, and rates of both sides are equal. Okay, so this is false statement. And in the third question, we are talking about water steam reacts with carbon to produce hydrogen and carbon monoxide. So we have, according to the following reaction, so in here we have gas state water, carbon solid, hydrogen gas, and CO gas. It's asking us the correct expression for Kc. As you guys may remember, you probably do, in Kc expression, we have products over reactants. So the right side is my products, the left side are my reactants. Okay, in Kc expression, we do not include solid or liquid phases. Okay, so that's why we're not going to include this carbon which is in solid state. So let's write it down. The Kc expression is looking like this. So you need to always put them in brackets. So we have on the product side, we have hydrogen, and the coefficient in front of it is 1. In front of CO is 1. Everybody is 1 in here. So if H2 has a coefficient of 1, it's going to have an exponent of 1. And then CO is 1. And then in the bottom, we have water with 1. Oh, we're going to ignore the ones and just going to keep it writing like this. So that's the answer for Kc expression. You need to don't forget the brackets. They need to always be there. So there is no these two concentrations are multiplied to each other. There is no addition sign. Okay, so this is incorrect. It is multiplication sign. So that's why the answer is gonna be B. Okay, so we move on to the next question. The equilibrium constant for this reaction is K. What's the equilibrium constant for the following reaction? As you guys see, the coefficients are halved in this one. So I'm just going to derive this equation for you guys. So the K is Kc. Kc for the first guy, the one given in here, is hydrogen iodide to the power of 2 because it has a coefficient of 2. And then hydrogen to the coefficient of 1. And iodine to the coefficient of 1. Now let's write the Kc, and this is equal to K. Okay, and now let's write the Kc of this guy. So we'll call this Kc1, we'll call this Kc2. So this is Hi divided by H2 to the power of 1/2, and then I2 to to the power of 1/2. So if you guys look at this too, you would see that Kc1 is actually related to Kc2 in this way. Okay? Because you see, if I will take the square of this, I will get the Kc1. So since Kc1 is K, Kc2 is going to be equal square root of K. As just a note for us as a tip, so if the coefficients are halved, then Kc is under square root. Okay? So that's why the answer is going to be D in this case. Now we move on to the question 5. It's asking us choose the correct options. The chemical equilibrium is dynamic. If you review all of our notes, you will see that it is dynamic because it's constantly exchanging one molecule from left side to the right side, so constant exchange. That's called dynamic exchange. And then there's an overall change in concentration of reactants and products in chemical equilibrium. Overall change in concentration. We said that the concentration stays the same even though there is constant exchange between them. So that's why the answer wrong for 2. And then we have temperature, pressure, or concentration of reactants or products can affect the equilibrium. It can affect because we talked about this in the Chatelier principle. So 1 and 3. And then let's check out the 4. Concentration of reactants and products are always equal. That is not right. We said that the ratio could be 90 to 10, 60 to 40, and 50 to 50. So it's not always, but it may be equal. That's why this statement is wrong. Okay, so we go into the next question. Question 6. Equilibrium constant for the reaction between sulfur and oxygen gas equals to this number at 300 Kelvin. So the temperature is given to you just as a side information. You're not going to use it. Now it's asking us the equilibrium constant for the reverse reaction. Okay, so the reverse reaction is this guy, right? SO2 and then sulfur S and O2 gas. So let's write the Kc for this guy. The Kc1 equals to SO2 in the brackets divided by O2, products over reactants. We're not going to include sulfur in solid state, okay? And then Kc for this guy is Kc2 is O2 divided by SO2. We didn't include the sulfur again. As you guys can notice from here, Kc1 equals to 1 over Kc2. Okay, so the inverse of the reaction is 1 over the Kc value. So from here we can say that Kc2 equals 1 over Kc1, which is this guy, right? The one in here. So 1 divided by 4.4, 10 to the power of 53, and then you use calculator to get the answer. This is not the last step. There is one more step to it, okay? Use the calculator to get the number in here. And we move on to the next question is question number 7. So over here, there's actually a typo in this equation. It says that the equilibrium reaches. It's not the right. We have equilibrium at we say we have equilibrium at minute 5. So the one in here, the graph, I have shown you in the class in our PowerPoint. This shows the concentration. So I want you to guys to pay attention over here. So this is the one about the brown and colorless gas that I discussed with you in the class. So you see the NO2 started from here, from 0. So the concentration for 0 for this guy, and the N2O4 is actually higher. It started at certain value, let's say 40. Okay, so it started from 40, but it went down, right? But NO2 went up. But at one point they reached and they never changed. So you see that the concentration is kind of stable here. So they reached equilibrium. But where did they reach equilibrium? If you look at here, the equilibrium is reached somewhere along here. At this point, it's no longer changing, which is approximately minute 2. Okay? So equilibrium was reached. They reached equilibrium at minute 2. Okay? But if you look at here, which one is our product and which one is our reactant? So if you really look into this, you would see that our reactant started. So reactant started, and then some of the reactant went towards the product. So reactant number decreased and product number increased. So in this case, our reactant was N2O4 and our product is NO2. And if you do balance, it looks like this. Okay, so reactant over product. So the answer for this one, it's asking x-axis. You see the axis in here. It's a concentration. That is right. This is one of the answers. The equilibrium reaches at minute 5. It's not correct. We didn't reach equilibrium at minute 1. X-axis is rate. So this is not rate. This is concentration, as we talked. The rate is going to be looking like this. Okay, so if I have my rate, we said that at equilibrium, both forward and reverse reaction reach the same rate. So forward and reverse reaction, they become at the same rate. This is the rate versus time graph, and this is the concentration versus time graph. So that's why the equilibrium reaches at minute 5. This is the answer is A and D, as C is incorrect. So we're going to go into the question 8 now. Which of the following changes will shift the position of equilibrium of this reaction in forward direction? Answer without justification will not be accepted. So it can be seen over there that this guy is in solid state, and then ammonia and hydrochloride is gaseous state. And because delta H is positive, it is endothermic reaction. Endothermic means that we put Q, heat, in the beginning, so this reaction will go forward. So we need to find out which of the following changes, decreasing the pressure or decreasing the temperature, will shift the reaction to forward. Position of this reaction, forward direction. Forward is from left to right. Okay? So let's do the decreasing the pressure. I want you guys to remember this. Decreasing pressure factor, pressure only affects gas molecules. Gas molecules. And it will make difference. It will make difference if we have different number of gas molecules when you compare products to reactants. Products to reactant. So right now, let's count the number of gas molecules we have. So in here we have 0. In here we have 0 molecules of gas on the left side. And we have 1 plus 1, we have 2 gas molecules. So the pressure will make a difference. Pressure will make a difference. So I'm going to be writing the pressure in here. We're going to make the table of disturbance, action, and result. Okay. So disturbance is decreasing the pressure. Okay. So we have decreasing the pressure. So from Chatelier principle, we know that we will counteract whatever the disturbance is. So we will try to increase the pressure. The system will try to increase the pressure. And to increase the pressure, we need to go to more molecules side, towards the side that has more gas molecules. So when you go to more molecules, more gas molecules equals to more pressure. So in here, because we have 0 on the left side, 2 on the right side, we will shift forward. Because we have 2 gas molecules on the right side if we decrease the pressure. Okay? If we decrease the pressure, the action will try to increase the pressure, which will happen by moving forward. You move forward, you increase the pressure as an action. Okay? Now we check the second one is decreasing the temperature. So decreasing the temperature we need to take into account whether the reaction is endothermic or exothermic. So in this case, we have endothermic, meaning that we have a heat on the left side, on reactant side. So heat is on the reactant side. So let's write the disturbance. So it is decreasing the temperature. So the temperature went down. Our action would be increasing the temperature, okay? So in order to increase the temperature, which side I will go, left or right? If I'll go left, you see there is no heat on the right side. But if I will go left, I will increase the temperature. So that means that in order to increase the temperature, I will go reverse, okay? So that's why the answer is going to be, we're going to be choosing one of these, and then we're going to explain. We needed to explain in here as well that why decreasing the temperature is making the reaction go reverse direction. Okay, so we go now to question number 9. We're talking about the N2O4 and 2NO2 molecules. In here, they are both gas state, okay? We have different number of gas molecules, so we have 1 here and we have 2 in here. That means that pressure will affect equilibrium. If we had the same number of gas molecules, pressure would not affect. Pressure will affect equilibrium. Okay? So now we're talking about which change in condition will cause the creation of colorless gas. So we know that N2O4 is colorless, while NO2 brown is a brown gas. Now it's asking us which condition will cause the creation of colorless gas. Okay, like we want to find the reaction that will drive our reaction reverse. We want to get the colorless. Let's do our table again. So we have disturbance, action, and results. Okay, so I got here increasing the volume. We know that pressure and volume are inversely related, right? From physics. If we increase the pressure, that means the volume will decrease. Okay, so it's saying us increasing the volume from here we know that increasing the volume means decreasing the pressure. So my disturbance is decreasing the pressure. My action would be counteracting that, which will be increasing the pressure. So in order to increase the pressure, I need to go to more molecule side. Okay, to increasing the pressure, more molecules, more gas molecules side. In this case, this will be going to forward and making brown gas forward. And we will make brown gas, which is not the answer we're looking for. Now let's talk about adding NO2, another factor. So we have the factors such as pressure, temperature, and concentration. Okay, so we talked about pressure, temperature. For temperature, we need to know whether it is endothermic or exothermic. And for pressure, we need to know number of gas molecules. Okay, and then for concentration, we need to know which one we're adding. So NO2, if I add NO2 in here, okay, NO2 increased, so my counteraction would be decreasing NO2. How can I decrease NO2? If I will go forward, I will make more NO2. But if I will go backwards, I'm going to use up the NO2, which is why I will make more colorless gas. Go in reverse. And I will make more colorless gas. This is the answer we're looking for. So you got to choose this and explain me why. Okay? Now we go into the next question, which is our question 10. So we got in here this Kc. I told you guys this means that products over reactants. And this means that this reaction is in equilibrium. So the main criteria of equilibrium is that we need to have arrows pointing towards right and left. Now let's write our products. We got A and we got B. But because we have coefficient of 3, this is going to be going 3 in front of it as a coefficient. The exponent will go as a coefficient. And then we got C on the left side and D on the left side. Because we have 2 in front of it, as an exponent, it will go as 2 coefficient, and D, the exponent, will go as coefficient in front of it. Okay, so this is the reaction we're looking for. This is a super easy question. I think a lot of you have answered this. Now we move on to the next question, which is this guy, question number 11. We're talking about making methanol from carbon monoxide and hydrogen. So it is asking us to deduce the equilibrium constant expression. Deduce means just write the equilibrium constant expression. So Kc, we go, is a product over reactants. What do I have as a product? We only consider gas states. So we got methanol, we put our bracket, okay, and then we go CO, and then we got hydrogen, and 2 coefficient will go as exponent. This is our Kc expression. Now we're talking about state effect of catalyst in the yield of yield and production amount of methanol. So we talked about this in the class, is that catalyst won't have any effect on equilibrium. Okay, equilibrium. It will speed up the process of achieving equilibrium. Speed up the process of achieving equilibrium, but no concentration change. I think most of you got this right. And then we go predict what would happen to the value of Kc if the pressure increased from 1 atmosphere to 5 atmosphere. Okay, so we talked about this, that Kc is only affected by temperature. The equilibrium will be, equilibrium is affected by temperature, pressure, and concentration, but Kc is only affected by temperature. Okay. On question 12, we're talking about the Haber process. It is making of the ammonia. We're combining nitrogen with hydrogen and making ammonia. Now it's asking in here, outline two characteristics of dynamic equilibrium. We could say rates of forward and backward reactions are equal. No, we could just say overall constant concentrations, and we could say closed system. We could also say reversible. Okay, and then in the second one it's asking, deduce the reverse equilibrium constant expression for the reaction. So the reverse reaction is this guy, given us N2 plus 3H2, and then the Kr, the Kc basically for this expression is N2 H2 to the power of 3, and then NH3 to the power of 2. We know that the coefficients go as exponents in here. Okay, so now it's asking predict what would happen to the position of equilibrium when the temperature is increased. Okay, we know that the reaction is exothermic. It is given to us. Exothermic means that the reaction will give out heat. Exo means out, endo means in. So the reaction will give out heat. For example, an explosion it is an exothermic reaction. Okay, so let's do the disturbance, action, and result table. So my disturbance is when the temperature is increased. So we increase the temperature, the action would be decreasing the temperature. So in order to decrease the temperature, which side I should go? To left or to right? As you guys can see, if I'll go to the right, I will have more temperature increase. But if I'll go left, I will decrease the temperature. So that's why it'll go reverse. Question 13, over here it's asking us to write down the Kc value. We have the product of SO2. We have the equilibrium concentrations. So let's write this down. Also, we see that delta H is negative, which means that it is exothermic reaction. Okay, that heat is coming out as a product. So let's write down the Kc expression, which is products over reactants. And then as a product, I have SO2 to the power of 1, and then O2 to the power of 1. And I'm not going to include sulfur because it is solid. And then I see that I have a SO2 value of 100, and then O2 value of 1. So that's why my Kc will equal to 1. Now it's asking us to deduce and calculate the equilibrium constant expression if the reaction coefficients are halved. We discussed above that if I half my coefficients, meaning if I will do like this, 1/2 sulfur in solid state, 1/2 oxygen in gas, giving me 1/2 SO2 in gas state, the Kc the Kc new will be the Kc of the old one in this under the square root, and my Kc old is going to be 100, so square root of 100 is 10. Okay, because if you write the Kc expression for this new guy, it will be looking like SO2 to the power of 1/2, and then O2 to the power of 1/2, which is basically this expression under the square root. Okay? And the third part, what information does the value of Kc in the first equation provide about the relative concentration of the product and reactants at equilibrium? So in the first equation, provide about relative concentration of product and reactants. So we know that Kc, product over reactants, which is SO2 over O2, is 100. If you use just this expression, we could say that SO2 is equals to O2 multiplied by 100, meaning that SO2 concentration is 100 times more than O2 concentration. Okay, now we move on to the fourth part. Explain why a decrease in temperature increased the value of equilibrium constant for the reaction above. I told you guys before that Kc value is only affected by temperature. So we have this reaction where sulfur is reacting with oxygen gas, and then we got SO2 gas coming out. And because it is exothermic, the Q is coming out as heat as a product. Okay, so let's do disturbance, action, and result table. My disturbance is temperature increases. Okay, so it is telling me that why a decrease in temperature, meaning that my disturbance is decreasing the temperature, increase the value of equilibrium constant expression. So if we go using our principle, I know that my disturbance is decreasing the temperature. My action would be increasing the temperature. Okay, so in order to increase the temperature, which side I'm gonna go? I'm gonna go towards the right side, because this way I will make more heat and my temperature will go up. So it's gonna go forward. And now if we write the Kc expression, this means that products over reactants, right? If I'm gonna go right, I'm gonna make more product and my reactant number will decrease, right? Because I will go towards the right side. And because my P increases, mathematically you can see the whole thing, the Kc expression is gonna increase. Okay, so that's why in exothermic reaction, when the temperature is decreased as a disturbance, the reaction Kc value will increase. Now we're moving on to the question 14. It's asking us to write the balanced chemical equation of the reaction above. The reaction we have is N2 reacting with oxygen giving out NO. So N2 reacting with O2 giving us NO. And if you do balance, we got it like this. This is the only thing you are asked to do in the first part. Now it's asking us deducing the equilibrium constant expression for the reaction above. We write Kc, products over reactants, and then we got NO to the power of 2, and then I got N2, and then O2 to the power of 1. This is my Kc expression. And then it's asking calculate the Kc value. So So I have the expression in here, so I'm just going to input the value. So NO, what is the NO? So I got 4 to the square, and then I got N2 and O2, which is 4 times 2. And then if you do math, 4, and then 4 divided by 2, it is 2. So the Kc expression equals to 2. Now it's telling us, suppose the equilibrium expression of the oxygen and nitrogen are as follows. Oxygen is 3 and nitrogen is 6. Using the Kc value above, given equilibrium constant expression, find the concentration of NO. We know that the Kc value stays the same when the concentration changes. The only thing that affects Kc is the temperature. So the concentration changed, so we write the same Kc expression. NO square N2 and O2 equals to 2. We know that it equals to 2. But now in this case, we're told that O2 is 3 and then N2 is 6. While NO is not given, it's asking us to find it. This is going to equal to 2. In this case, we will find it by doing the math. 6 times 3 times 2, which is 36. And then NO would be 6. We'll take the NO2 under the square 36, and this gives us 6. Okay, that's the answer for the fourth part. Now we're going into the 15th question. So in here, the red blood cell contained a pigment called hemoglobin. So I showed you guys this picture. So hemoglobin binds with oxygen and makes this product, hemoglobin binded oxygen. Oxygen molecules are carried to individual cells into the body tissue where they are released. The binding of oxygen is a reversible endothermic reaction. Endothermic means that we will put in heat to the reactant side. Endo means in. We put it inside the reaction heat. For the first part, define the term equilibrium. We say closed system, reversible, dynamic, this kind of equal rates of forward and backward reaction. So these are enough for us to term equilibrium. For second part, explain why increasing the temperature decreases the affinity attraction of hemoglobin for oxygen. So what they're asking is, hemoglobin is getting affected by temperature, hemoglobin capture. So affinity attraction is that hemoglobin no longer attaches that well to oxygen as well as before. Now we will solve this together with you guys. Let's do the Chatelier principle because it's saying increasing the temperature. So disturbance, action, and result table. It's telling us increasing the temperature. So increasing the temperature is my disturbance. My action would be decreasing the temperature. So in order to decrease the temperature, I need to go to forward side, right? Because if I'll go backward, I will release more heat, which is not the one I'm looking for. I need to decrease the temperature, so I'm going to go forward. There's less temperature there, so it's going to go forward. And in the forward reaction, what do you see as a product? Hemoglobin and oxygen are separating from each other. So that means that their attraction is decreasing. Attraction decreases. That's it. You need to explain this. And then it's telling us to deduct the forward and reverse reaction Kc expressions. So the forward reaction is the one that is given above. So I'm going to write Kc equals to P over R. So what do we have as a product? Hemoglobin and oxygen. So I got hemoglobin and then oxygen. And then in the bottom I have hemoglobin, oxygen. This is one compound by itself. And the Kr is literally just opposite of that, because the reverse reaction is like this, right? Hemoglobin plus oxygen giving us hemoglobin, oxygen binded warm. And then if I write the products of reactants for this guy, what do I have as a product? This one. So hemoglobin binded oxygen divided by hemoglobin multiplied by oxygen. Okay, and we go into the fourth part of this, which is our last question. Scientist claims to have developed a new catalyst which increased the yield product amount of oxygen. Comment on the claim by scientist. We told you guys that catalyst only speeds up the process of achieving equilibrium. It does not affect concentration. So that's why the claim is false. Okay, so that's it, guys, for the equilibrium. I think it will be useful for your exam preparation. Thank you very much.